Okay, thank you very much. Good morning, everyone. Let me make a new announcement. One of the students on the other side asked me for my notes because she had some problems to distinguish between Y and G, and that's bad. And so I'm willing to give the notes, and I think Danielle is going to forward them. These are the notes of the whole course. I'm still not completely sure if I'm going to be able to do everything, but you can keep the notes. But these are notes for me. It's not a book. It's not notes for students. These are the notes I use. Yeah, so probably, or maybe I say things that are not in the notes, but I think on the other side, it's going to be useful, at least for the proofs and so on. So I have no problem with that. So instead of starting with the exercises, let me finish chapter 1, and then we do exercises, and then we do a little break. Okay. So I finished chapter 1. Because it's really not much, and it's a nice place to cut and start with the exercises. Yeah. Okay. So we were counting elements in the ball, yeah, around the neutral element, and there, this is where we stopped, and we were able to at least agree on an upper bound of this number, which is 1 over 1 minus m or r plus 1, 1 minus n. So we sum the geometric progression essentially, and that's all. So groups, finally generated groups. There's finite are bounded geometry. And that's a prototype. Okay. So that is what you should have in your mind as a prototype, a standard example. And the spaces we are going to deal with are of this kind. Okay. Let me point out here what happens if you have infinitely many generators. As a remark, the number of generators is infinite, and you can think of examples of that, with infinite copies of finite group, for instance. Well, then, of course, the ball of radius 1 at any point, say E, the element is infinite. And this corresponds to a graph which is not locally finite. So this is E. You have, so to say, infinitely many edges going out of this element, any element. Yeah? So this is not locally finite. Another way of saying this is that the group, any element, has infinitely many neighbors at distance 1. Yeah, and this is something I want to avoid here. Yeah, so this is not the case. And so let me end with a definition, which is the growth function, and say a few comments. So it's about 10 minutes, I think, what I want to say. So definition. Let G be finitely generated, and the growth function for this group is just counting how many elements sit into sit inside the ball of radius r at E. And the interesting notion here is what happens when r grows. Yeah. So how many points get inside these balls when r is growing? So the growth function is a function that depends on the group and on the generating step, and goes from n to n. And how is it defined? So beta of r, take r a number. Beta of r is just the cardinality of this group. And the interesting question, which helps to classify groups, is to look at the asymptotic behavior of this function. Let me give you a few examples. So of course, the question is, what happens when r grows? Okay. And of course, the first example is the easiest one. Then the ball radius are centered at the origin. I'm writing that adequately, so the neutral element is 0. And that's just okay. So the cardinality is, so the growth function in this case, beta of r is equal to 2r plus 1. So if you want a polynomial of degree 1 in R. So the variable is R. So what is the second easiest example? Z2. And we will see that the growth of the function is again a polynomial, and now of degree 2. In general, Zn grows like a polynomial of degree n. Okay? So maybe this is illustrative. So let me do the picture here. So here we have the neutral element. And here we have this goes, it's 3, but let me think of r. Then we have this here, this here, this here. 1, 3. Okay. These dots here are the ball, is the ball of radius 3 in the picture that you can, in your imagination, think of r. This is minus r, r, minus r. And it's a ball like an L1 node. If you think of functional analysis, it's the ball you get when you take the L1 node. Yeah? And the reason is you need, you know that the path length metric or the work length metric is exactly the same. I need to go to r steps to here, and so 1, 2, 3. So this is in, but this is not in anymore. So it's not an L infinity norm, it's just an L1. And I can sum in this way. So I can consider this wing here. I can consider this wing here. It's like a windmill. Okay, I can consider this and this one. So I slice the unit ball into four wings and an extra dot, which is the origin. So how many numbers do I have? And then I have to count 4 times because I have 4 wings. This one here, this one here, this one here, and this one here. Okay? And so you sum essentially r times r minus 1. So r times corresponds to the horizontal axis, and then you get 1 less, this point, and this point. 2 plus 2. And this we can sum also. And altogether, you get 2r squared. So this is Gauss, the sum. Oops. This is Gauss, the sum of the first r numbers. And so in the end, you get. Okay, I'm not trying to do it for free set free. Yeah, my limitation is taken in drawing. Yeah, but in general, for G equals N, beta grows binomial And now the last example will be the free group, and we start the exercises with a daily graph. Maybe we are doing actually the first exercise of chapter 1. So let me just show you what happens with the free group. Yeah, and we will see that the function there grows exponentially, and that's a very important difference between Zn, which is an amenable group, as we are going to see in chapter 2, and the free group. Okay. This is my last example, and then I tell you a few things about growth of groups, general things, and then we stop this part. Let me maybe recommend there is a whole chapter. If you like these ideas to analyze the groups as empirically but the growth function, so there is a whole chapter. See, there is book. I don't remember now exactly what the chapter was. I think I know that. It's chapter 6. It's really nicely written. Yeah, so fine.
No lo has dicho, pero demasiado que los generadores la S en los cursos son los obvios.
Muy bien, muy bien. Yeah. Yeah, that's important because, and this is going to be an issue. The growth functions beta depends on the group and on the generators, like the Cayley graph. So the growth function, as I wrote it, is still not the end object. We have to define an equivalence class of growth functions. I'm not going to do this in this course, but you can read that in Lewis' book. Yeah. But maybe the example of the free group on 2 generators. So the free group on 2 generators is just a group of all words you can do with this alphabet. No relation except the trivial one. A minus 1 is the neutral element, and all other combinations. There are no other relations. Yeah, and of course you need them because you have a group. It's not a semana. Okay. So of relation. That's the obviously. Okay, and this is the most non-commutative group you can imagine, and it's kind of opposite to the Z2. You have commutation, not between the generators, any element. That's an abelian group. That's highly non-abelian. At the other extreme. So let me just to count the number of elements in the board. Let me just give you a graphical picture of the free group. Yeah? Here you have another one. That's why I asked you for the book. Maybe you have seen this. It's the cover of this book by Novak Yu. Yeah? So this is another, like a fractal. That's another representation. That's the Cayley graph. That's the solution to the first exercise in the sheet. Okay, but let me just turn it a bit around. Remember, Cayley graphs are graphs, so the geometry doesn't matter at which point you put, in which direction you put the edges. Okay, so this is E. And from E, you can go with the generators to 4 points. A inverse, to B, and to B inverse. Okay? And now, from each of these 4 legs, you can go to 3 other places. Yeah? If you multiply by A inverse, you go back to E. But otherwise, you turn to a different vertex. Not because remember again, there are no relations. So you have 3 legs going out of here. You have 3 legs going out of here. You have 3 legs going out of here. And B to the minus 1 turns you back to the point you already have. Okay? And so on and so forth. Yes. And here you have again 3, and so on and so forth. It's clear it's going to be an exponential growth. Yeah? And so on. So this would be a 3 squared, and so on. So how many, remember again, R is a natural number. So this is 1 plus 4. Yeah. And now you start getting powers of 3. Yeah? 4 times 3. Yeah. Here you get 4 times 3 legs. In the next generation, you get 4 times. You get 4 times square, and then you get here 3 times r2 minus 2 because you lose 2 generations in the first 2 steps. Okay, and that's again a geometric progression. And now think again that the variable, let me put it in yellow, the variable is the radius. Okay. And so altogether, if you compute, you sum this geometric progression, you get 2 times 1 plus 2 times 2 times r to the 2 times 3 r to the 1 minus. So it's exponential. And for many, many years, it was not clear if there is a growth in groups which is between polynomial and exponential. And there is. Yeah? And this was 70s. Olshansky, I think, developed or constructed examples of intermediate growth between polynomial and exponential. Okay, so let me say a few things, and then I start to be a question.
One question.
Yes.
El crecimiento del grupo se puede entender como una medida de la conmutabilidad del grupo o no tiene relación.
No. La conmutatividad está relacionada, pero no puedes leer o sea, puedes ver la torsión del grupo, pero la conmutatividad no necesariamente. De hecho, grupos promediables, ¿no? Tienen crecimiento polinomial. O sea, el polinomio no te dice si es conmutativo. O si quieres es un invariante, pero no es muy, o sea, no es muy rígido. Puede haber muchos grupos que tengan crecimiento exponencial, ¿no? Okay. Okay, remarks, final remarks. As I told you, beta is a function of t and x. And this is very nicely explained in Lewis' book. So you have to define a kind of equivalence relation. Yeah? You have to first control what happens if I change from S to S prime. What kind of mistake or what kind of error is the change of a finite generating set introducing? And then you identify these growth functions. Because a growth function cannot depend asymptotically on the generating set. Yeah, and this is the notion of quasi. Introduce the notion of quasi equivalence or growth functions where you essentially identify growth functions with different, the same group with different generating sets. Yeah, this is introducing a multiplicative and additive error, and you can identify. And then you define, if you want, an equivalence class, and that's the right object. It's more or less like what we did with the Cayley graph. Yeah? And then you can show. So the first statement is, if you have two groups which are quasi-equivalent or quasi-isometric, this was our notion, then the corresponding functions are the same. So the growth functions, yeah, this equivalence class of growth functions must be the same. And this shows you, this is a kind of application that Z2 cannot be quasi-isometric. That's not possible. We computed that one has a polynomial growth, the other is exponential. Yeah, so this is a way of applying these growth functions. Also, Zn isometric to Zn, even only if n is equal to n. Okay, so these are little applications. I have not shown it. It's in chapter 6 of this book, and many more things about these growth functions. but I would like to stop here and start with the exercises. I mean, I finished chapter 1, so I need to start today the second part with amenability. Is there any question here? It's a kind of appetizer of growth of functions. But I stop here. Any question?
When we speak of quasi-isometric between groups in general, we are assuming that they are finally generated.
Yes. Yes. I mean, you can go beyond, but in this course, I mean, you can define quasi-isometries between the not finally generated groups. That's possible, but I'm not doing this here. Otherwise, I will stick to the first chapter until the end, and I want to move on.
We define the growth and the length of a group, and obviously if it's a same group.
That's my research. Have you looked at this? No. Yeah, but since you ask, I'm very happy to answer. The point, the difference, the key difference between a group and a semi-group is the following. So the concrete answer is, I don't know. I think it's not a useful notion. First of all, you don't have the metrics are not invariant. So you have, it does matter if I am at the identity, which you don't have in general, in semi-groups, you may have a 0, or if you are far away from it. So there is a lack of uniformity in semi-groups. That's a big, big, big problem. Yeah. And the difference between groups and semi-groups is that if I have a set in the group and I multiply by G, and cardinal, yeah, and the cardinality of F is equal to the cardinality of GF. Yeah? Because you have an inverse for semi-groups. Yeah? So if you have a semi-group, and you have let me say S for the semi-group, then if I move F by an element little s, then it may happen that this guy is bigger than this. So in particular, a semi-group, yeah, a semi-group. So this means that the action is not injected. Yeah? That's the huge difference. And semi-groups are geometrically, this is really present-day research. What is the geometry of a semi-group? Yeah? You don't have a regular graph associated to it. And maybe the extreme case is you may have a 0, a multiplicative 0. So 0 times F. This may even have infinitely many elements. So this is 1. Yeah, because you kill everything. So the dynamics, the motion inside the semi-group is highly non-injective. And this is a mess. Yeah? So I don't know if you can define a growth function in this way. Yeah? Because the dynamics is not injective. You can define graphs, and there are many kinds of graphs. And my experience is that semi-groups, I mean, the Cayley graphs of a group is a regular graph, which is a very special kind of graph. Here you have all possible graphs appear as Cayley graphs, if you want, of a semi-group. That's the message. So the complexity is huge. Passing from groups to semi-groups geometrically is like passing from regular graphs to any possible graph, which is a huge complexity. But that's a long story. We can talk if you are interested. Okay, so let me move on to the exercises. So we have the chance to go back to the quasi-isometries, which I assume most of you see them for the first time, so we can practice a bit more. Ah. Okay. So let me see. There are a few typos, so I prepared the exercises for the first time. So it's also a quasi-isometric version of the real test. I tell you some typos. And if you see some, just let me know. Okay. Okay, the Cayley graph of a cyclic group over 4, I think you know. Yeah, so the cyclic group, so let me just say 1, 1, C4 is just 0, 1. Let me write it algebraically, and it's obviously generated by 1 and 3, which is the inverse of 1, and the Cayley graph is a cycle. This is 0, 1. I can go from 0 to 1 with 1, and I can go from 1 to 0 just adding 3. The free group generators, I draw a tree for you in the previous exercise. If you look in internet, there is a really in the wiki page, there is a lot of nice things about concerning the Cayley graph of the free. Yeah, so I think this is okay. So 1, 2, I'm going to do some exercises in more detail. Yeah. But 1, 2 is just saying that I introduced the BC quasi-isometries. Yeah, and it doesn't really matter. You can take a CC if you just take the biggest one. If P is bigger than C, then you take a BB quasi-isometry. You get exactly the same upper and lower bounds of the image. So let me maybe write there the definition of quasi-isometry. Maybe you don't quite remember. Let me put here for the exercises again the window. So you have two metric spaces. This is a quasi-isometry. And then you have this quasi-isometric embedding where you bound essentially sorry, let's put a bit more of space. Otherwise, B, and then you have 1 over C distance B, and then you can change B by C if you want. Yeah, so this was one condition. This is the quasi-isometric embedding condition. And then you have two different ways. You need a way back, the G I wrote you, or you need to have an M-dense image. Yeah? So this was the first condition. And to be really a quasi-isometry, you have to be able to turn back from Y to X. Yeah, and so f of X is, if you want, M. Okay, and that means that any point in Y, a ball of radius M around that point in Y contains at least one point of the image. Yeah, and you can take also M equal to C. Just take the biggest. Yeah, so these were the two conditions. Let me just do. So this was 1, 2. You see, 10 minutes on the exercises. But maybe you want 3. This is this is a nice example, I think, that illustrates a lot what may go wrong with quasi-isometrics. This is something one has to get accustomed to. So imagine that you have Fp, a metric space, yeah, and F has finite diameter. So let me just put an X. With you consider all the distances between X, all distances in X. Then you take the sum of these numbers, and that's fine. Put it P, the diameter. Yeah? And the question is, show please that all metric spaces with finite diameter are quasi-isometric. In particular, all finite spaces are quasi-isometric. And this is what I told you. Anything bounded is a part. Yeah? That's the idea I was trying to pass the first day, the first motivation. Yeah. Yeah, I think that the quasi-isometry was kind here. So imagine that you have X Y, also Y, finite diameter. And yeah, you have something bounded here. That's X, and you have something Y. This is also bounded. I mean, finite diameter. Yeah. So this is the diameter is D. I can just put this here. This is D, and this is D prime. If you want. And so what can it be there, the isometric? You don't care, you have many as points you have here. Yeah? So you take a special point here, say, why not? You don't care because you have finite diameter. And you can distinguish just one X naught. Yeah, and then F goes from this Y, and you send every X Y naught. And G goes from Y to X. And G of Y is X naught. Then you can check that these are in fact quasi-isometric. Yeah, it's very easy. These are quasi-isometric because the distance in X and X prime, that's the distance between the same points is 0. So these inequalities are trivial. Yeah. And you can take B as the diameter. And then you get the other one. Yeah? Take, for instance, take C1 and B equal to B. And so you have the distance between X and X prime is essentially smaller or equal to 0, and that's a trivial inequality. Okay, and the other way around again. And of course, you still, so this is condition A, it's trivial, and the other condition is it's also trivial. Let me use the original definition I used with the F and the G's, because I have them here so nicely written. E density is exactly the same. So if I go first with G, so I have to I have to map a point in the target space, and I have to compare. Remember that the composition was not the identity, but was close to the identity. This was my original definition of quasi-isometric. But so if I send y to x naught, and x naught is sent to y naught. So essentially, I'm comparing the distance between these two things. And that's clear. That's dominated by the diameter. And the diameter of the target space. Yeah. So any pair of sets which have finite diameter are quasi-isometric. Never mind what kind of things you have. Any pair of finite sets is quasi-isometric. Yeah. Okay. There is another one. Maybe I don't do it because I want to go to exercise 1.5, which I will not finish today, but at least I will send you. I will do some parts of this exercise. But let me also tell you. Maybe this was part A of 1.3. Let me say a few things about part B, which is also very nice and improves the intuition about these kind of quasi-isometric. You have to get accustomed. I'm still on the way to get accustomed to them. Did some of you try? Since tomorrow we don't have lecture, maybe we can interact a bit more on the exercises next week. Next week I will be a free man, but on Thursday, did somebody try some of these exercises?
Yes, I saw the first one.
The first one.
The first one.
The first one. Okay.
I have a question regarding the last one, the first one.
A question concerning the
exercise 1.4.
Exercise 1 of 4.
1.4.
Yeah, okay, yeah, 1.4, I prepared the solution, which is proposition. Wait a minute, 5, 10, and there's 2. So I didn't want to do it now. Maybe can we discuss it later? Because on the break you can show me. And but this is one of the standard exercises the lecturer does when he has or she has no time to. But the solution in this book is really step by step. It's not very difficult, but we can comment it later. Okay. What I wanted to say is a few words on this one here. So if you have two metric spaces, you can say bounded geometry in the category we are thinking of. Yeah, and this is a generic one, and then you have the finite diameter. Then it's very easy to see that the injection sending an element x times n and not, and not a distinguished point in this finite diameter set. And once you take a projection onto x back, forgetting about this fiber, if you want. This is an projection, and this is a projection. All of these are quasi-isometric. Yeah? That's a very nice picture. So in other words, any finite diameter perturbation of any set is quasi-invariant, quasi-isometric to the original. Yeah, and that's actually the inverse. So this is the F, and this is the G of the definition. Yeah, just try it. But the picture is that whenever you have a set, you can perturb it by a finite set or a finite diameter set, and you remain on the same class. That's very useful when you do this kind of computation. And that's a very nice example. You can try to check the definitions. Okay. So let me say a few words on 1.5. Yeah, because this is something I'm going to need in the second lecture. Okay. So, did some of you try 1.5? There is a mistake. Did you? Sorry? Ah, ese no lo he visto.
B, la segunda inclusión es en la bola de centro, o sea, de radio 2TR más T cuadrado.
T cuadrado, sí, sí.
Y...
Okay, typos for 1.5. Let's start with the easy. Maybe at the end of the course, I can send you a corrected exercise sheet as a souvenir. Okay? So, the pre-image of the ball is again, so the pre-image of a bounded set is bounded. That's very important. And that's contained in the ball of
Perdón, me han pedido antes desde el chat que si puedes evitar utilizar el corte de la pizarra porque se proyectan dos pantallas distintas. Pero vamos,
sí, sí.
Con cara y los...
Yo un momento que... So this one. Okay. That's okay. Again, bounded. This is a point which is somewhere in the pre-image. Yeah? And now the thing is that you have to scale the radius. Now you pay the price of using quasi-isometries, but the scaling, the correct scaling is 2CR plus C². Is this what you say? Okay, so this is the first time. Indeed, so this was indeed. Indeed. I'm not going to do the exercise D, so let me postpone it because I myself am not completely sure about the proof. And I realized just 10 minutes. And to avoid confusion, we believe for the moment on part B. I will tell you, I will give you a reason for that. But there is a very important thing. That has to be finite, very important. Okay. And in fact, we are going to use it in this way. Yeah? So this is finite. So this double inclusion for me means finite. If you want, it's finite. And BC, however, is the fattening. Yeah, it's what is called the C fattening. Now you just fatten the set in this way. And that's another type. So this is a typo. This one is a typo, it was an X, and here. Okay. Good. So let's start with 1.5.8. So I hope everyone knows what is the difference between pre-image and inverse function.
I think you will define the
Yeah, that's the next one. We are going to define it in the next chapter, but I should have defined it in the new version. I already changed. Okay? Let me just definition. Of outer boundaries. Okay, so what is it? You have XD metric space, and the idea again, a picture is the following: you have your space X here, this part of the blackboard, and you have the set A, and this guy here this is just the outer boundary of A with radius R. Okay, and I'm spending some minutes because this is saving some time from chapter 2. So I'm defining it here. It should have been defined on the exercise sheet. Okay, so what is it? The picture is very clear. I'm saying outer boundary, and that's the outer boundary. Okay, and so this is the picture, this is the idea, the inclusion. What is the formal definition? Well, very easy. It's the set of X in the space, and outer means not in A. So I'm only looking outside the set. So I just take out A, such that the distance between X and set is below or equal to R. And this distance between a point and a set, you know how it is defined through the infimum or minimum. Is a parameter. You collect all distances from X to points in A, and then you take the infimum or the minimum. Okay? So that's the outer boundary. So the statement of the problem was scaling sets and boundaries with quasi-isometric. I don't tell you what the boundary is. Yeah? It could, in fact, everything I say for convenience, I'm using the outer boundary, but you can do the kind of boundary going into the set up to radius R. It's completely the same. Yeah, but you have to stick to one, and I don't want to mess you up with too many possibilities. But you don't care if you go R units inside the set. It's exactly the same. Okay, so 1.8. So if you have a set in X, and you have a quasi-isometry X1, quasi-isometry. And I think you know the definition of pre-image, or should I write it for you? When I was your age, I was confused about the difference between inverse and pre-image. Huh? The pre-image is always the same. Okay. So if you don't complain, I continue. So what is the relation between this one? So you move the set into Y and then you turn it back by the pre-image. And if you have a B in Y, It's just the other way. This inequality, this inclusion, which turns out an inequality of cardinalities, we are going to use the next hour. If you start in the target space with a set T, you take it back to to X, and then push it forward again, then you end up with something which is bigger. These inclusions are obvious, just using the definition of being. I hope nobody has a problem of the one we can discuss it later. The question was, are these inclusions proper or not? Can you give me an example? Can you give me an example of a set where the inclusion is proper? Have you tried?
Space of more than 1 point.
Yes. Yeah. For instance, you take X to be finite, okay, and more than 1 point. Yeah, and then you take F to send everything to Y. It's just 1. This is what you need. So you see again, finite perturbations are making the counterexamples. Okay? And this is really an important idea in this business. Okay. So maybe you can try this. It's really easy. It's just a fine. Makes no sense that I go through details here. Just check. And of course, if you have some doubts, let me know. B, I would like to did somebody have problems with part B, which is essentially saying that a bounded set is moved into a bounded set by a quasi-isometry, and the pre-image of a bounded set is always a bounded set. Yeah. I mean, tomorrow we don't have lectures. Maybe you can try these things and tell me if you have problems. Okay. Let me say a few words and then I do the break because it's 12 o'clock and I need to move on. Maybe I can tell you the idea of the factoring. Why do we need a factoring? Because this is what it's a good place to stop. And here. Okay, let me say a few words on B, and we will come back to this exercise hopefully on Thursday. Yeah. So what is the problem? So F is a finite set in one. Okay. So have phi here. You have a set here F. It's finite, so you have finitely many points in here. And you want to take it back to X. Yeah, you want to take a pre-image of this guy. And the problem is, that the pre-image F may be empty. Because quasi-isometries are not injective and not surjective, so that's a problem. And that's this breaks all the inequalities I wanted to show. Yeah? And so the way out, it's always the same in this business, is to fatten the set. You know, the problem is that maybe this is an f of x. This here is an f of x prime, but they never touch f. Yeah? So to be sure to have elements from the image, you have to fatten f. Yeah? And so the idea is that you make the set fatter, and then you are. So this set here is the fattening, everything. Yeah? So this is the fattening of the C fattening of F, which is the union lies in F of balls with radius C. So C, remember, quasi-isometry guarantees that at distance C, you have a point in the image of the points Y. Yeah? So this is called a C fattening. C fattening of. And now you know that the image intersected with the C fattening of the set is non-empty. So this means that maybe so this guy here, this white dot is Y. Sorry, from the other side, then you know that on this ball of radius C, you have an image. That's the reason. And then you define F hat to be the pre-image of the fattening of the C fattening. That's the correct way to pull back a setting Y through our quasi-isometry to get the non-trivial inequalities. Okay. This is the explanation of this set. Yeah? So you are in X. Let me put it in blue because it's related to the blue picture there. That's F hat, which is the pre-image of the pattern with radius on. Okay. And what we will need in the next lecture is to analyze what happens to the outer boundary of this guy here. We are going to show that amenability, which is the starting point of the next chapter, is invariant under quasi-isometries, meaning that if Y is amenable, it's an amenable group. Think of the group as a metric space. If Y is an amenable group and you have a quasi-isometry from X to Y, we are able to pull back to X the sets that have certain properties, which we are going to analyze now. Okay, so this is the usage, and we are going to analyze outer boundaries of this F hat. These are, and then we want to know what happens. One of the points here is what happens to the outer boundary of F hat. Okay, so this is at least the idea. And if you want to solve this problem, just think first of what happens at the finite set level. Yeah? So I think it's quite illustrative for this problem to consider the exercise. What happens if analyze what happens if X is finite and Y is take the usual isometry sending x from some distinguished. Just try to understand what is the set, a hat, in this very particular case. And you will see that the inequalities I'm proposing in the exercise, and we are going to do this in a minute, but in this very special case, they are true. And they are not true if you don't fatten. Yeah, this fails. So the fattening is absolutely necessary. Okay, so let me stop it here. I haven't done this exercise. Maybe we can come back to that on Thursday. Okay, so let me do a 5-minute break, and then we start with chapter 2. I am late, yeah, so I planned this second chapter to finish today. So I will probably need the full hour on Thursday, yeah, to finish chapter 2 and have enough time to speak about operators. Okay, but since I'm jumping from one topic to the other, any topic is like a black hole. You can get in and not come out. Yeah, and amenability and property A are again 2 black holes. I hope I can stay away from the horizon. Okay, so question: who has heard about the notion of amenability? Okay, and how did you do you remember how it was defined?
Not really, because it was like a thing I need to know, but I didn't pay a lot of attention.
Who else? Do you remember how it was introduced? You and me. Okay, very good. Somebody else? Somebody has heard the notion of Fermat, Fermat sequence or Fermat set? Okay, so the problem with amenability is, if you look at the book by Nate Brown and Takawazawa, it says that amenability has 10 to the 10 different characterizations. So I'm using one of these. And they are really huge. You can characterize amenability through the spectrum of the Laplacian in a Riemannian covering of the. The covering group is going to be amenable if the Laplacian has 0 in the spectrum, which is incredible. And you can characterize amenability through means. And I'm going to do it through an isoperimetric condition. Yeah, this is the notion of formalism. Okay, so that's the isoperimetric problem. You know what it is. You have a curve with fixed size, yeah, fixed length, and you are asking what area, what region has the biggest area with a given fixed boundary, yeah, and you know that if you have a curve of length L, say, then the area of the circle is the maximal area compared to any polygon of this fixed size of the curve. Yeah, this is the isoperimetric problem. Okay, so this is going to be the way I'm going to introduce amenability. And then I will tell you a few things. Okay, so from all these, I take one, which is related to this isoperimetric conditional presentation. So one, amenability. Let me write as an isoperimetric condition. Okay, so first I define for you amenability for groups, and then for metric spaces, I comment how this definition is. Okay, so definition. So you have a group which is finitely generated. And this guy is amenable. If for each epsilon bigger than 0, I promised you epsilons, and from now on you will have a lot of them. And each finite set, f for finite. I hope you can see it on the other side. Let me write it this way. And again. There exists an F for Fernando. So Fernando was the guy that translated von Neumann's definition in terms of means, which was the original one, into a combinatorial condition. Yeah. So this is a Fernando set, which is again finite and not empty. Yeah. So the cardinality of F is finite and certainly not empty, because we are going to divide by the cardinality of F. Yeah. And such that it now comes the isometric like condition. So this is the symmetric difference. I'm going to make a picture in a minute. You can think of the numerator as a boundary. And this is the area. So you want to make this number here very small. So the boundary is compared to the inside epsilon. Okay. For all t in this finite set. So you're saying that your group is amenable. If you can, for any epsilon, for any tolerance, error tolerance epsilon, you can find such a corner set, which is finite and not empty, that has a boundary, essentially a boundary compared to the inside, which is a polar epsilon. Yeah? And these guys are called finite sets. Very important and interesting. So this F is called the finite set. This is the isoperimetric ratio. And yeah, maybe a picture is, so you have epsilon given, and you have your finite set T, and then you have to get me an F, which contains, of course, only finitely many points. This is an F. Then you move it. So this is G times F, with G in this. I like to see GF as a dynamics, where you move your set around. Yeah, it's a kind of dynamics. And this is the symmetric difference. Yeah, this is not the Laplacian, it's the symmetric difference. Which is nothing else than what is in one set, but not in the other. Yeah, so it's essentially a kind of boundary-like set. Okay, so what is in F and not in GF, so this guy is here. And what is in GF but not in F. So this here is the symmetric difference. Okay. And so this blue strips here compared to the size of it is epsilon. That's a point. Remarks? The first one is metric space availability. This is coined essentially with the same idea. The only difference is that you have no dynamics to move around because a metric space seems to be static. Yeah, but still, let me write here metric space. Metric space availability. So take, let's see the bounded geometry. Remember again, bounded geometry means that the balls of radius are uniformly bounded. Yeah, you move them around and you don't grow the cardinality of these balls. That's our context. Is available. That's the notion we are defining. If for every epsilon, every r positive, this is going to be the radius of the outer boundary. So we are comparing the isoperimetric ratio is comparing boundary with the inside, and this we can do easily. Yeah? Here, if there exists, if for every r and every epsilon there exists a corner set, which is in X, and it's non-empty, very important too. And if you remember my first part of the lecture, I told you that we are going to, one of the leitmotifs of this course is the finite approximation. Amenable groups or amenable metric spaces allow a very nice finite approximation through corner sets. Okay? Such that, let me just put a hat here. Yeah, because we are in the metric space scenario. Yeah? And such that the outer boundary of F hat compared to F hat is smooth. Yeah. Okay. And the outer boundary I don't need to define anymore. Yeah. So if you want a picture, your corner set here, this is F hat. Yeah, so you give me R, you give me the error, and I find for you a corner set such that the outer boundary again is small compared to the inside. Yeah? So you see, it's not exactly the same, but it's the same idea. It's an isoperimetric condition. Okay, so this is my first remark. What is my second remark?
Can I ask a question?
Yeah, sure.
What does the notation, the double convention mean?
That's, yeah, this means a finite.
Okay.
Yeah, notation if you want. And double contain A means the cardinality of the local versus global version. Okay, there is an exercise to chapter 2. If you want, this is a local definition. That's if you study continuity of functions. You start given an epsilon, you want to find a delta depending on epsilon, uniformly depends. This is a local definition. You can define continuity through limits if you want. Right? It's not exactly the same always, but the idea is this one. Yeah? And so this is a local version, local definition in terms of epsilons and r's, or in terms of epsilons and finite dynamics. But there is a global version. If you don't like epsilons and you want to present it in a complex this idea, you can use the definition of the limit. Yeah. So G or XP is amenable if there exists a sequence of corner sets sequence of non-empty finite corner sets such that the limit n goes to infinity of that carries 0 for all r. One of the exercises is to convince yourself that local definition and the global one are the same. It's a really useful exercise for you. Yeah? And my last comment is going back to Neumann, 1929. So this Furner characterization is due, as you can imagine, to Furner. And okay, I'm with you in a minute. Let me just write the third remark. Okay, tell me. No, so you have a sequence, in fact. You have a sequence, and this is true for any r. Yeah? In the version here, you get the isometric relation. So this over the inside of the Fn tends to 0 for anything. Yeah? Okay, very useful this exercise. And let me tell you that if you want to prove, and that's why I choose the local version, the way to prove is to use the local one. That's what we are going to use. That's why I put it as a primary definition. Okay. Amenability. This notion is beautiful Neumann. Yeah, in the year. That's Neumann. And the year 29. And it was a time where the Banach-Tarski paradox that tells you that you can take an orange, break it into 5 pieces, you rotate the pieces on isometry, you glue the rotated pieces again, and you get 2 oranges of the same size. Yeah? That's true. And von Neumann realized that the rotations in 3 dimensions have an amenable discrete subgroup. And that guy is very bad. It's not amenable. Yeah? I'm going to show it to you. So amenability was introduced by von Neumann through the existence definition through the existence of an invariant probability measure on the group of mu. This is the power set, so you are able to measure all subsets of the group, and you send them 0, 1. Yeah, it's a finitely additive. Let me not write it because we are not using this version. Finitely additive total probability measure of the group. So in particular, the whole guy has weight 1. That's not so strong, but it's invariant under translation, which is so through a measure. Let me avoid finitely additive total blah blah, which is invariant under, which is invariant. What do I mean by that? If you take any subset A of the group and you move it, so A is in the group, G is a subset in the group, and this is just a element. Yeah? And von Neumann called it in German Mittelbar, which has a promediable in Spanish, promediable. Puedes tomar promedios. This is the invariant mean. This is what you need to take the means. In English, it's meanable. And you know, humor of mathematicians, and then Marlon Day came and just, let me see. So this was Day. Funny guy. So he moved this A in the front. The point is, and this has no translation because amenable means in Spanish dócil, bueno, obediente, no? So this makes sense in English. This makes sense in English, but there is a connotation of that. So this is the origin. And you cannot do it in German and Spanish. I don't know. But you see, now you know what amenable is. Yeah? And nowadays, everyone, even in Spanish, you see conferences, amenabilidad de grupos, which is, well, everybody knows what is meant. And the notion was invented exactly to distinguish groups that allow paradoxical decompositions, like in the Banach-Tarski paradox. The free group is not amenable, because it allows paradoxical decompositions, and is the reason behind the fact that you have this decomposition of the sphere into 5 pieces, rotated, give you 2 spheres. Okay, so this was the joke. Let me maybe mention, at least compare to Van Nylon. So this definition of amenability, the one I gave you there, is of the year 55. So this is 29, which was the time of the Banach-Tarski paradox. Okay, further to how can I get a measure out of the Palmer sequence I had there in my global version? Well, it's by intersection. No, that's my definition. This is a probability measure. So if A is everything, then you get a 1 here. So the group, it's a probability measure. The only difference is that it's not quite invariant. Because when you move these things, you are not invariant. And now you have a weak star compactness argument. So you know this family of measures related to the sequence of Palmer sets. By weak star compactness, you have converging subsequences. And these cluster points, these are really invariant. These are almost invariant, but you do an error. Yeah? So the existence of the measure, if you give me the Palmer set, is guaranteed by the weak star compactness argument. Very standard. I don't want to come into details. Okay, so let me let me give you 2 examples, 2 quick examples, and maybe state the main theorem of this section, which is that amenability is a quasi-isometric invariant. Yeah, that's a very important topic. It's a very important result. But first, let me give you maybe some exercises, and tomorrow you have time, examples. Well, they don't have time because they have lectures in the morning and afternoon. Okay.
Not everyone is going to every course.
So the symmetric difference of these 2 courses are going to do the exercise. Yeah. Okay, so the cheapest example is G is finite, then it is amenable. Okay, very cheap. What is the Palmer set? Yeah, remember, typical of Palmer sets, non-empty and finite, because we are going to approximate the group through finite sets that have moderate growth. Yeah, when you move them, the boundary does not grow too much. This is the intuitive idea. Yeah, let me take, for instance, the metric space, because we need it later. Let me take the metric space. So think of the group as a metric space. Another way I introduced amenability for groups and amenability for metric space. Every group is amenable if and only if its Cayley graph thought as a metric space is amenable to. Okay, so in this case, the outer boundary of F is empty. So the isoperimetric condition is trivial because you have 0 divided by the size of the group, which is 0, and it's always below epsilon. Yeah, because epsilon is epsilon. Okay, if G is there, then check that the color sets are scale codes. Given epsilon positive, you can always think that epsilon is 1 over n. Okay. And then you check that these balls, that this guy here is a function. Oh, put it this way. That's enough. Now you check it. Yeah, so this is 0. This is an r, and this is minus an r. Okay. And you compute given r positive. Yeah, you compute with this isoperimetric equation. You see that it's essentially 1 over n, and that's smaller or equal than 1 over n, and that was epsilon. Okay, you check. Let me just conclude the example with to complete the picture with Panaftarsky paradox. And let me do the third example. F2 is not an union. So that you have, well, let me say that every abelian group, every finite group is amenable, every abelian group, semi-direct products of amenable groups are again amenable. It's a very stable class of groups. But F2 is not amenable. And I'm using von Neumann's definition because it's much easier. Yeah, so you believe that they are equivalent. I gave you a reason why they are equivalent, how to get measures from color sets. And it's very nice to give you this proof. It's very easy, and probably this is one of the things you will remember of this course. Let me introduce the reduced words that start with A. Okay? So maybe I haven't said it. The free group is just all words that you can construct with the alphabet A, B. Yeah? So remember again. So any word you can do with this alphabet is an element in the group, and the product is just to put them together. Yeah? And this here are the reduced words that start with A. Reduced means that if there is a possible cancellation, you do it. Yeah. So it's like thinking of a fraction 1/2. This we accept as a fraction, but we don't want to have 2 over 4. That's not reduced. And you can always reduce a word. So if when they come together, you hit an A with an I minus 1, you just cancel it. Okay? Well, then we are almost done. Because we can decompose the free group into 5 pieces. And that is in the origin of why the orange of the unit sphere is decomposed into 5 pieces. Yeah. then the free group from two generators can be written as the identity. This is a disjoint union. All words that start with A, all words that start with A inverse reduced words. It's important. So the identity, I don't accept that you write me the identity as A times A to the minus 1. That's not reduced. So this guy lives alone. E to the minus 1. Because any word is either the identity starts with A inverse, or B inverse. Yeah, that's obvious. But if you want, I can rewrite this in this way. Or in this way. Okay. So the free group can be decomposed as a disjoint union of 5 pieces or of 2, because these are the words that start with A, and these are the words that do not start with A. Yeah. So imagine a word being here. The only thing I know, I don't know what happens afterwards, but we start with A. So, sorry, with A inverse. And since the word is reduced, I cannot have an A here. I can have an A inverse, or a B inverse. But not an A, because it's reduced. And so if I multiply this word with A, I'm sure that I'm not starting with A. So this is another decomposition. Yeah? The same group. Yeah? And then assume that F2 is amenable. Then we have, after von Neumann, an invariant probability measure. So we have, and there exists an invariant probability measure mu. Okay, what happens with that? It's a probability measure. Every guy, the full group measures 1. And this is, how do I do it? Okay. This is a disjoint union, so the measure of this guy is the sum of the measure. But the measure is invariant, so I can just cancel this guy here. So the sum of this piece plus this piece is 1. And in the same way, 1 is the sum of B, the words that start with B, plus the words of B times the words that start with B inverse. But again, by invariance, I can cancel this here. Now I come to this 5-piece decomposition. The measure of F2 is 1, but contains 2 pieces that measure 1. So it's bigger or equal. I don't care what the identity measures. Yeah, so I get now 1 is equal to the measure of F2. Which is a contradiction. Yeah, because these 2 together measure 1. These 2 together measure 1. And I lose something. Maybe there is some weight on the identity, but on the neutral element. But I don't care. Okay, so you get the contradiction. F2 is not a mean. I don't want to prove it with promises. Okay, so let me now come at least to the to the final theorem of this section, and we start then to first day with property A, which is a generalization of this section. So does anybody of you have heard about this? Those interested in groups, this is a very standard argument, okay, to prove that F2 is not a minimum. Yeah, so we have Zn as an abelian extreme, F2 as a non-abelian extreme, Zn as an abelian extreme, Fn as an extreme non-abelian group. Zn is amenable, Fn is highly non-amenable. Yeah? And it's the reason behind these kind of paradox. Okay, so let me delete here and state the final theorem. Which is a very important one that motivated actually me giving this course on this topic. There were other possibilities, but this is one of the important ones. So let G and H finitely generated discrete groups. That are quasi-isometric, such that G is quasi-isometric with K. Then, if K is amenable, G, this guy here in the beginning, cannot be non-amenable. Yeah? So that's what we call quasi-isometric invariant notion. Yeah? And if H is amenable, then so is G.
Yeah. La cache volante H.
So, yeah. Aquí también. Okay. So for H, you have a final set, and you want to pull it back. That's exactly exercise 1.5 of the first part. Yeah, that's our strategy. And yeah, I think I have 5 minutes. At least maybe I can send you the. Maybe it's better to send the proof. But still, let me just write the strategy. The idea of this group is the following. H has further sets, and we want to pull them back. Yeah? So you have F. That's a quasi-isometry. Isometry. And H has polynomials. And the idea is to pull the polynomials back to X to show that, to G, and to show that G is again amenable. But we have to massage with these polynomials, not because we have quasi-isometries. It would be trivial if you have a full isometry. Okay, so idea that polynomials from H to G. Okay. So the first thing is assume F H, the target space, is on R prime epsilon prime. Yeah, I promised you a lot of epsilons. Everything is now epsilon prime or r prime polar sets. What do I mean by that? Is that I think I do it metrically. Yeah. So the outer boundary of the polar set F in cardinality compared against the inside is smaller than epsilon prime. I do a prime because then I have to rescale later. I don't want to give you the solution now, we will find it together. Yeah? This is going to be a function of r and epsilon. Yeah? So we can assume that we have an r prime epsilon prime polar set on the target space. And now let the given r positive and epsilon. Yeah, this is going to work on X, sorry, on G. Yeah. Show that there exists R epsilon order set F hat for G. And then this R prime and epsilon prime will depend on R and epsilon. Yeah? This is telling me in the metric space scenario that the group G is on. And that's exactly what I need to do. And that was the reason for putting this exercise 1. I told you that we need to massage a bit the set. You cannot just put it back. So we have y here. And we have x here. And we have the polar set here. And we cannot just put it back with the pre-image of the quasi-isometric because it may be empty. Yeah? Maybe no point here comes from a point in G. Yeah? And that's the reason why we have to take the patterning. That's the patterning set, which we call this here, which is the union of rise in F, balls, radius C. And C is it's a quasi-isometry with C dense image. With C dense. Okay. So that's why I pattern with C. I can do it. Yeah, I know if I go far away enough, I will hit some point in the image. And now what is the polar set? Here, it's exactly the F hat we had in this exercise. It's the pre-image and the quasi-isometry of the flattened curve. Yes. And now I'm a bit over time. Maybe I can, because I don't want to hurry here. That's exactly the nice proof. Maybe let me stop here and say play. I write the claim and maybe I start here next week. You forgive me. Yeah, we don't. F hat is our epsilon underneath the polar set. Taking epsilon prime to be epsilon over n squared. Okay, This is the M that appears in 153. Exercise 153. And R prime C on C. And this is a quasi-isometry, if you want, C. So that's a quasi-isometry. I can take the constants to be equal, and I can also even take C to be equal to that. Oh, maybe I have an M. I think it's an M. Or anyway, I can tell you. Here. No. I can take this also equal to C. And the M comes from the exercise. Yeah? And so next Thursday, I'm going to show you that this is really this guy here, the fullback of the pattern performance doesn't do. Yeah, and for this, I will leave these exercises. But I don't want to hurry. This is almost over 1, and you have a long afternoon. Thank you very much.